Okay, so we're back. Temporary bit of a panic there. I'm going to move some stuff around here. I'm learning. I just learned something new. My camera here only takes 15-minute video segments. I looked down at the time and realized I didn't have that much time anymore. I thought I'd inadvertently paused and had lost some video. And anyway, so I'm going to have to splice a whole bunch of little videos together, and that's okay. I can make that work. So now I know 15-minute segments. So here we are again. Okay, so we talked about the head form, and I'm probably just going to cut this part out. We talked about the head form, okay? So we talked about all the different forms of the general energy equation. Okay? So it can take different forms, and all the way back up here to the Bernoulli equation. Right. Now, from there, if we talk about then, I'm trying to as I'm pausing here, what I'm trying to do is I'm trying to think, okay, was there anything else in chapter 5 that we talked about? And I don't think there is. I think that's we've gotten pretty close to everything there out of chapter 5. That brings us then into chapter 6. Chapter 6 talks about the conservation of momentum. Right, chapter 6 being the conservation of momentum. Now, that derives from the basic idea that it's Newton's second law that says that if we add up all of the forces acting on a system, then that represents the change in the momentum for that system with respect to time. Now, if the mass is constant, if I've got a single particle and the mass is constant, the mass comes out of this differential, and then I'm just dealing with the change in the speed of that particle with respect to time, and that's just acceleration. So from physics 1, F is equal to ma is what we remember. Yeah, it's actually Newton's second law tells us the net force will actually cause a change in, I believe Newton's words was the quality of motion of a system with respect to time. In this case, we're talking about a system of infinite particles, of fluid particles moving. So they're all going to be moving in different directions. They're all going to have different masses. It becomes much more complex when we're talking about a fluid system, but one of the tools we have to go after this is the Reynolds transport theorem. And the Reynolds transport theorem tells us, making sure I'm still on the screen here, Reynolds transport theorem tells us that the change in a conserved quantity, in this case the momentum of our system, right? So it's impossible to track all of the particles within a fluid system. But what we can do is we can look at the change in that quantity for a control volume. Add to it the total rate at which that quantity goes out of the control volume, and subtract the total rate at which that quantity, in this case the momentum, comes into the control volume. And as we said earlier, the change for the system, can just simply be represented by, if we add up all of the forces acting on the control volume, and then make sure we include the momentum change, any momentum change for fluid particles coming into or out of the system, and that will serve just fine to figure out unknown forces, or vice versa, use unknown forces to figure out changes in momentum. Now, most of the time, if the control volume is stationary, control volume stationary, then the change in momentum for the control volume is 0. And that's a common thing that we'll deal with. In fact, I'll put it this way. I'm only going to test you on situations where we're trying to find a force, or we're trying to find the conditions where the control volume is stationary. I think that's more practical, unless you're going into literally into rocket science or aerospace or aerospace engineering. Then you are actually dealing with situations where we're trying to accelerate the control volume through a momentum change in and out. But if that's not the case, most of us are probably mechanicals, maybe some petroleums and civils. We're dealing with situations of how much force is required to keep this thing stationary. So that's, for me, it's a little more practical, and that's probably what we're going to do the most of. So, what that means then is this sum of forces represents all forces applied to the control volume. And as we've seen, that is pressure times area. And it's, unless you want to include the atmospheric pressure all the way around, you probably want to work in gauge pressure. And it's to deal with the gauge pressure times area. It can be weights, and reaction forces, which is often but not always, what we're trying to find is what are the forces being applied to this control volume in order to keep this control volume stationary. That's, again, the common, as we've seen, that's the common scenario we'll look at for problems. Is what is the reaction force required to keep this stationary? Not saying that's the only problem I'm going to ask you. I'm just saying it's a common one. Okay? All right. From there, then we talked about Chapter 7, right? And that is, Chapter 7 is where we deal with the Buckingham PI Theorem, the concept of repeating variables and dimensionless quantities. Right? So we said that that was a multi-step process. I'm going to pull my textbook out here. Your exam will be open book for a number of reasons. So again, remember in your textbook in Chapter 7, there's a couple of tables there that walk you through this process. So I'd rather show that than I would you guys try to decipher my writing. So I apologize here. I'm flipping through to find the right tables. Part of me says I should edit this out in video software, and part of me says, no, we may not even do that. So here we go. I'm going to make sure I'm still on the screen. Right, so Table 7.2 in your text talks about the steps for the Buckingham PI Theorem process. And then there's this one step that says, step 4 is choose the repeating parameters. Which parameters are we going to use to build our dimensionless terms? And then Table 7.3 goes through a lot of information about how do you pick good repeaters. And I don't want to go through all that here in a short video. But then step 6. This is kind of the least important one. Step 6 here. I'm not going to count a problem wrong if you don't do step 6, as long as you do step 5 and you give me dimensionless pi terms and the appropriate number. Step 6 is kind of a nice icing on the cake to do, where you go look in Table 7.5 and you look for common established pi terms. And so You can say, hey, did I find a new pi term, or did I find one? And we've seen more than once a common pi term would be the Reynolds number, right, which is on this page. The Reynolds number. So the Reynolds number is a common pi term anytime I've got a phenomena that is controlled by speed, a length, density of the fluid, and viscosity of the fluid. Those terms together combine to become a dimensionless term. And it's not uncommon that we'll end up with the inverse of the Reynolds number or the Reynolds number as one of our pi terms. We're dealing with things like that. Right? We've seen, remember we said that the drag force of a object within a flowing fluid. So if you take a model of a car and put it out in a wind tunnel, or if you stand out on a windy day, that the force of that wind blowing over a body is a function of essentially the size of the object. We'll say a diameter, the density of the fluid, the viscosity of the fluid, the speed of the fluid. Okay. And what ends up happening is you end up getting the coefficient of drag ends up, we find, to be a function. And again, you see I've got a length, density, viscosity, and speed. That combines to become the Reynolds number. So we find that the drag coefficient, a dimensionless quantity we can use to describe the force, the drag force on an object, is going to be a function of the Reynolds number. And we've done this one in class. There's no sense in going back through that. And again, in Chapter 8, when we talk about the energy loss within a piping system, and in class we did the shear stress on piping, right, due to viscous fluid flowing over, is going to be a function of the diameter of the pipe. This quantity we call epsilon, that's the roughness of the pipe, density, viscosity, and speed. Okay. Well, the energy loss, which is going to be a function of this tau, so this is a function, the energy loss is a function of the shear stress on the pipe. So it's also going to be a function, this energy loss is also going to be a function of all of these terms. So but the energy loss is also a function of one more term, the length of pipe. So the length of pipe, the diameter of the pipe, the roughness of the pipe, this epsilon term, that's length, the average length of how rough the pipe is, right? And then these other terms, the density of the fluid, viscosity of the fluid, the speed of the fluid. And so what we'll find is that this ends up being, this energy loss ends up being a function of the dimensionless quantity associated with the energy loss, ends up being a function of length over diameter, epsilon over diameter, and the Reynolds number. So this energy loss, at least a dimensionless quantity, and I don't remember this one off the top of my head, we've not derived it in a while, is going to be a function of these three dimensionless terms instead of these six-dimension terms. And the idea of Buckingham PI Theorem, it's this theory that says any phenomena, so we've shown several phenomena here, that may be a function of multiple parameters, you can reduce that when you turn everything dimensionless. So the dimensionless version of the drag force, being the drag coefficient, is a function of far fewer parameters than the dimensioned quantity drag force is a function of these dimension quantities. And so there in your text, the whole point of Chapter 7 is learning the process of saying, if this is a function of all these things, well, because there are 5 things here, right? There's 5 things here, and there's 3 dimensions here, right? There's mass, length, and time, right? This is mass, length, and time. This is mass, length, and time, and these others mass, and length, length, and time. There are 3 dimensions going on here. So that tells us that we could write 2 pi terms.